Yeah, hello. So my name is Buhai, and I'm a PhD student, a third-year PhD student at ETH Zurich. And I'm going to present a recent paper that we had at Stock this year on opportunity threshold for semi-random planted click. So we are motivated, first of all, by the standard max click problem, which is just you're given a worst case graph and you want to find a k click in it, a click of size k. And as everyone knows, this is an NP complete problem, an NP hard problem. So you cannot hope to do something really efficient there. So then people sometimes study an average case version of this, which is the planted click problem, which is the basic idea here is that you have a random graph in which each edge appears with probability half. You select a subset of k vertices and you put a click on them. And then you want to find the click. So let's see how we can depict this. So I want to depict the graph as follows, with a partitioning it into S star and V minus S star. So S star is composed of k vertices, and V minus S star is composed of n minus k vertices. And of course, there are also edges between S star and V minus S star. So far, there's nothing special about this partition. Well, in the planted click setting, you assume that S star is a k click, so a click of size k. And for all the other edges in the graph that are outside the click, you assume that they are random, that each edge is generated independently with probability half. So this holds for the edges between S star and V minus S star, and also for every edge in V minus S star. And the goal is, given such a graph, to find S star, to find the vertices in the graph that form the k click. And this is called the planted click. So it turns out that how easy this is to do depends on how large k is. So let's see what is known. For k smaller than 2 log n, it's actually known that it's impossible to solve this problem, because in the random portion of the graph, you're going to have with high probability a click of size 2 log n. So then it's impossible for you to even tell which was the planted click and which is a click that just arises naturally. And on the other hand, for k larger, much larger than 2 log n, it's possible to solve the problem from an information theoretic point of view, but not necessarily efficiently. So let's see what is known about efficient algorithms. Well, when k is at least root 10 log n, it's enough actually to just output the k vertices that have the highest degree. And these are going to be with high probability the vertices in the planted click. And this can actually be improved to any constant times root n with an algorithm that rounds the second eigenvector of the adjacency matrix of the graph. But basically, that's it for polynomial time algorithms. So, okay, what happens? What can we hope when k is between 2 log n and root n? What happens then when the click is not so big? Well, unfortunately, there are some restricted lower bounds. In particular, it's known that it's hard to solve the problem with sum of squares programs, which is a big class of convex programs, a very powerful class of convex programs that kind of encompass all average case algorithms, basically, and also pretty much every estimation algorithm that exists. And yeah, and I should also mention that this is taken as evidence that the problem is probably really hard computationally for k between 2 log n and root n. And there also exists actually another type of lower bound called the statistical query lower bound, on which Elena actually worked. Yeah, I wanted to mention that. So, but when k, the good news here is that when k is at least root n, you can solve the problem in polytime. And this is something that's not possible for worst case clicks, because it's an NP complete problem, an NP hard problem. So then the question here is, can you hope to do something similar in a more adversarial setting without using that all the graph is random outside the click? And that's how we come to semi-random planted clicks model. So the model that we study here in our paper is specifically one introduced by Feiga and Kilian, and it looks as follows. So you still have a k click that's planted in a graph, but now, for the vertices between S star and V minus S star, we assume that these edges are generated randomly with probability 1/2, but then an adversary can remove an arbitrary subset of them. So that's between S star and V minus S star. But in V minus S star, we assume that this graph is completely adversarial. Like an adversary can choose it arbitrarily, and an adversary can choose it adaptively based on the randomness, based on how the random cut between S star and V minus S star looks. So you cannot assume anything at all about V minus S star. So basically, the only thing that's not adversarial in this model is that the cut between S star and V minus S star is not so bad. It's random, and then the adversary is only allowed to delete, but not to add edges there. So this is, yeah, closest to a worst case graph. So what do we want to do? Yes?
There's a question in the chat. There's a question in the chat.
Yes, okay, let me see. Is there a size restriction on the number of? No, the relations can be arbitrary, but I mean, if you delete everything, then it's going to be trivial to detect to find the connected component as the click. Yeah. So what's the goal here? Unfortunately, in this model, it's actually impossible to recover S star at all, simply because in V minus S star, the adversary could simulate up to n over k, basically k clicks, such that between each of them, you have a random cut. So then it's really impossible to tell which is S star and which is one of them. So this is irrespective of the size of k. So then our goal is going to be to recover a small list of k clicks that includes S star. So specifically, we'll want to recover n over k clicks such that S star is guaranteed to be in this list. So why n over k of them? Well, as I said, the adversary can simulate up to n over k clicks in the adversarial part. And okay, it turns out that we can actually achieve n over k. So that's the optimal. Okay, so let's see what is known about this problem. Well, compared to the standard planted click, now it's actually impossible to solve the problem for any k smaller than √10. And this was showed by Steinhardt. It's impossible information theoretically to recover a small list that's guaranteed to include the true click. And conversely, for k larger than √10 log n, it's possible to solve the problem, but not necessarily efficiently. So what about polytime algorithms? Well, Charikar, Steinhardt, and Valiant gave an algorithm that works for k at least n to the 2/3 times some log factors. And this was later improved by Mackenzie, Mehta, and Trevisan to n to the 2/3 without the log factors. And basically, up to our paper, that's all that was known about polynomial time algorithms. So it really remained an open question whether you can still solve the problem at the same threshold of √10 that you can do for the standard random planted click problem. And our paper comes close to solving this question. So basically what we show is that you can approach √10 arbitrarily. We show that basically, yeah, you can solve the problem for k larger than n to the 1/2 plus 1 over t in time n to the O of t. So you should think of t as a large constant, and as t gets larger and larger, you get closer and closer in the exponent to n to the 1/2, which is √10. So that is the main result. And yeah, in a theorem form, it just says the same. For any t, given algorithm that runs in time n to the t, and for k larger than n to the 1/2 plus 1 over t, we output a list. So the list size is 1 plus little o of 1 times n over k. So it's almost exactly n over k. And it's a list of k clicks such that the true click is part of it. Yeah, so this is the result. And now I want to talk a bit about the techniques that we use to achieve this result. So let's start by thinking about what would even be an inefficient algorithm here. And from this slide, I'll just assume for simplicity that there are no adversarial deletions. So I'm assuming that, that the cut between S star and V minus S star is completely random without deletions, but V minus S star is still arbitrary. And it turns out that it's easy to put this back in the algorithm. So for an inefficient algorithm, you might think that you just output all the k clicks. But this actually outputs potentially an exponentially sized list. Because, for example, V minus S star can be the complete graph. So then you'll output exponentially many things. And recall that the goal is to output at most O of n over k clicks. So it's not trivial even to get an inefficient algorithm. What helps us is the following claim, proved by Steinhardt, which is that with high probability, S star intersects every other k click in the graph in at most log n vertices. So if you have just any other k click, let's say this red blob here, the intersection with S star is small. And the intuition for this is that if you have such a k click that intersects S star in a lot of vertices, it means that there are a lot of very structured edges going between S star and V minus S star. But we assume that the cut between S star and V minus S star is random. So by a probabilistic argument, you can show that with high probability, like the maximum intersection you're going to see is log n. And the second claim is actually just one that allows us to get a small list size. It's just an inclusion-exclusion argument. So it says that for k at least √10 times some L, if you have a list of k-clicks such that the intersection of any two is at most L, then the maximum number of such k-clicks is n over k. So in a sense, what this is saying is that if you have many k-clicks which are almost disjoint, then you can put at most n over k of them. So this is really a trivial proof for this claim. And then these two claims actually give us an algorithm, a very inefficient algorithm, but an algorithm that works for k larger than root n log n, which is very good. So you just output all the k-clicks that intersect every other k-click in the graph in at most log n vertices. So you implement this by, checking if something is a k-click and then checking all the other k-clicks and making sure that the intersection is small. So first of all, note that this outputs S star, because we know by the first claim that S star intersects every other k-click in at most log n vertices. So it's going to be part of the output. And we know that everything that we output, all the clicks that we output, will have intersection at most log n between themselves by the definition of what we output. So then by the second claim, when k is at least root n log n, the size of the output will, will output at most 10 over k k-clicks. So this is an inefficient but correct algorithm for this problem. And now we're going to look at how we can possibly make something like this efficient. We're going to start from this. And we're going to note that the key structural property that we used was that S star intersects every other k-click in the graph in at most L vertices, where L was log n for us. So it turns out, this is kind of a big step, that if we can certify this property, that S star intersects every other k-click in few vertices, if we can certify this in time n to the t, then you can also create a sum of squares program, which is a convex program of size n to the t, that gives you an algorithm that runs in time n to the O of t, and that works for any k at least root n times L. So the k larger than root n times L, this just comes from the inclusion-exclusion claim on the previous slide. The big thing here is kind of that, if you have a certificate of a property that guarantees small intersection, then you can also get an algorithm that runs in the same time that it takes you to certify, basically. And this kind of paradigm of going, from certification to an algorithm has been used in some other instances. It's well known in, the sum of squares community. I cite here a paper that does it for linear regression, for example. It was done a lot in estimation settings. But yeah, we are able to do this. But then the question is, even if you are able to do what I put here in the box, how do you get the first step? How do you get the certificate? And that's what I'm going to talk for the rest of the talk. So basically what we are able to do is we're able to certify this property. We're able to certify in time n to the t that L, like the intersection of a k-click with S star, it's at most n to the 1 over t. So now if you plug this L into the box, into the algorithm on the right-hand side of the box, it gives you an algorithm that runs in time n to the t and works for k at least root n times n to the 1 over t, basically. So let's see what this certification actually means. So how do you certify that S star intersects all the other k-clicks in at most L vertices? So first of all, what does it even mean to certify? You can assume now that you know what S star is. Let's assume you know exactly where S star is. And you just want to prove to someone efficiently that every other k-click that intersects S star intersects it with a small intersection. And you want this proof to be basically based on explicit properties of the graph. You cannot say, the proof is that the cut is random. You need to prove it to say, look at this graph, look at these properties of the graph. Therefore, all intersections are small. So let's see how we can prove something. How can you possibly prove efficiently something like this? And we're going to start with a few observations. First of all, if you just look at the cut between S star and V minus S star, and you ignore the connections in S star and V minus S star, this is basically just a random bipartite graph with k vertices on the left, S star, and then minus k vertices on the right, V minus S star. And if a k-click intersects S star in L vertices, then it actually means that this random bipartite graph contains an L by k minus L biclick. Where by biclick, I mean the following. Let's suppose that you have a 5-click here. Everything on the left must be connected to everything on the right for this biclick that's red. So we call this structure a 2x3 biclick. So it's basically a complete graph, a complete bipartite graph with 2 vertices on the left, 3 on the right. So all I'm saying is that if a k-click intersects S star in L vertices, it means that in this entire random bipartite graph, you must have an L by k minus L biclick. So then it actually suffices to certify that a random k by n minus k bipartite graph does not contain any L by k minus L biclicks, because this automatically implies that any intersection with S star must have size less than L. So let's see how we can prove something like this. And for simplicity, I'm going to consider k by n bipartite graph and L by k biclicks, just for simplicity of notation. So let's start with a very simple example, which is a so-called spectral certificate. So consider the adjacency matrix of this random bipartite graph. So you have a k by n bipartite graph, and you have its adjacency matrix, which is a k by n matrix. And I'm going to put +1 if there's an edge, and -1 if there's no edge. Okay, then I want to say that I use as a certificate the fact that the spectral norm of B is at most √10. So for a random bipartite graph, this holds with high probability. And I claim that this fact alone, the fact that the spectral norm of B is small, is enough to say something about biclicks without using anything else about the randomness in the graph. So let's see what it implies. How do you use this spectral norm? So suppose that there is actually an L by K biclick in this bipartite graph. And let X and Y be the indicators of the vertices that are in the biclick on the left-hand side and the right-hand side. Then X transpose BY, this will actually select all the edges that are part of the biclick. And we know that this is a biclick, so all those edges are present. So they're going to be +1. So the X transpose BY is just the number of edges in the biclick. So it's L times K. And you can also get an upper bound on the same quantity. So X transpose BY is at most norm of X, norm of Y, norm of B. So norm of X and norm of Y are √L and √K, respectively. And the norm of B by the certificate is √10. So if you combine these, you get that L is upper bounded by n over k, by just combining these two facts here, which means that the size of a biclick in this random bipartite graph is at most n over k by k. So the left-hand side of the biclick cannot be larger than n over k. So this is very exciting because you can get a proof about how large the biclicks can be by just using this certificate, just using the spectral norm of the adjacency matrix. And if you check what algorithm this certificate gives, well, it gives you an algorithm that will work when k is at least √n times √L. So in our case, √n times √n over k. So if you simplify everything, this gives an algorithm that works for k at least n to the 2/3, which is exactly what the previous results had. Which is also interesting because the previous results definitely don't talk about certificates for refuting biclicks or stuff like that. But their results up to log factors can be captured by this spectral certificate. So now let me just very briefly mention what is our certificate, with which we achieve our result. This is a higher degree and non-spectral certificate. So again, consider the adjacency matrix and construct a tensored version of this adjacency matrix. So now we're going to create a much bigger matrix that has k to the t rows. Each row is indexed by a set of at most t indices that represent rows in B. And the point is that this row of M is just obtained by multiplying element-wise the rows in B selected by this set. So as an example, if the first 3 rows of B look like this, they're ±1, then M at the index, the row of M corresponding to the set 1 to 3 is obtained by just multiplying the element-wise, across each column, by just multiplying these 3 rows of B. So we created this big matrix M. And as a certificate, we use the following. We use that the inner product of any 2 rows of M is at most √T times N. So for us, T will be a constant. So we're basically saying that it's all at most like √N. So basically that these rows continue to have an inner product that looks random. Because for two completely random ±1 vectors, if you take the inner product, it's going to be bounded by √N. So we're saying that we use as a certificate the fact that the rows of this matrix are nearly orthogonal. And I got to say, if you just try to use the spectral norm of this matrix M, it does nothing. It gives you no advantage. So we cannot use just the spectral certificate for this tensored matrix. So now let's just very quickly see what this implies. Suppose again that you have an L by K biclick and consider its indicators. Now, Y will be the indicator for the right-hand side of the biclick, but X now must be an indicator for M. So X is going to be 1 for all the sets of size at most T that are completely included in the biclick, in the left-hand side of the biclick. So then X transpose MY is going to be L to the T times K. Because how many subsets of size at most T are there of the left-hand side of the biclic, which has size L? Well, it's roughly L to the T. And now, the last step is, as before, we want to also obtain an upper bound on the same quantity and derive a certificate from this. I'm not going to go through the calculation. I'm just going to say that this definitely uses at one point our certificate, that the inner products of rows of M are small. And it gives, that X transpose My is at most root L to the T K N. And if you combine these together, you get that L is at most N over K to the 1 over T. So there are no biclics of size larger than N over K to the 1 over T, which finally gives the algorithm that we want. So the algorithm works for K larger than root N times root L. L for us is N over K to the 1 over T, the upper bound on this, on the intersection with S star. And therefore, we get an algorithm that works for K larger than N to the 1/2 plus 1 over T. And yes, this is the result. So we obtain this certificate. This certificate gives us an algorithm, and that's it. Sorry for going slightly over time, and thank you.
Thank you. Questions?
I'm not that familiar with this semi-planted problem. Does it have any implications?
The point here is that, okay, standard planted clicks are hard. They're NP card. So people study average case. So they started, the planted click.
Yeah.
And, for planted click, then it's easy at root N. And you want to understand how closely can you get to a worst case. Like somewhere trying to understand what really makes the max click problem hard. Yeah. And in our case, we show basically that as long as you assume that just the cut between the click and the rest is kind of random, you can solve. You can find click of size root N at least.
Yeah, understood the technique.
Yeah.
Also have a quick question. I no longer do phase transitions, but in an earlier life, I did. And when I saw your talk, I thought of, reasons for which landscape reasons for phase transitions. And I've actually Googled and I saw a recent paper by David Gabarnik on uniqueness gap property for planted click and some sort of explanation for failure of sum of squares and things like that. So is there a deeper connection? Do you know more of this direction, or is it something that is so I found, as I said, there are like some results in phase transitions which suggest sometimes that in terms of clustering, whenever you have solutions in clusters, the problems are going to be difficult for like Markov chains and stuff like that.
Yeah, so this is the overlap graph property, right? Or something like that?
Mm-hmm. Yeah.
Yes, so I'm not extremely familiar with this. So I know, again, as I said, I know that for this problem there, some squares lower bounds and statistical query lower bounds. I haven't seen this last paper on overlap graph properties, so I'm not sure.
Mm-hmm.
I do know that it's widely believed that the planted click problem is hard for K less than root 10, and that actually there are a lot of hardness results in average case complexity that are reductions from planted click. So basically they assume that planted click is hard, and they base the hardness of many other problems based on the fact that planted click is hard. So that's a line of work I know a bit about.
Mm-hmm. I've sent in the chat the link to the paper that I'm talking about.
Okay, I will take a look. Okay, and I see that someone asked in the chat whether this can be generalized for other types of planted graph structures. Right now, like the exact same thing holds just for what we said. It actually also holds like if I assume that in the cut the probabilities are 1/2, and we also have some results if the probabilities are not exactly 1/2. But an interesting question is, can you do this for planted dense subgraphs, for example, which is a harder problem basically than planted click, or things like stochastic block models, which are kind of similar to this kind of thing. I'm not aware of any such results. We are looking at some of these things, so we are actively working or starting to take a look at some of these, but I'm not aware of any existing results so far. Yeah, so I'm not aware of anything for SBMs. I have recently started to look a bit at semi-random planted SBMs. Yeah.
Other questions? And let's thank the speaker again. And the next presentation is by